Hello, everyone, and welcome back to our series on knowledge tracing. Today, we're diving deep into one of the most powerful models in the field, deep knowledge tracing, or DKT. By the end of this video, you'll have a crystal clear understanding of how this teacher with a smart notebook works, step by step. Here's what we'll cover today. We'll start by recalling the limitations of traditional models like BKT. Then, I'll use a simple analogy to explain the core idea of DKT. We'll break down its key components, and then, for the first time, we'll do a simplified manual calculation to see it in action. Finally, we'll discuss what DKT actually learns, how it compares to BKT, and how we can extend it for even more powerful applications. Let's start with the problem. Imagine our student Xiao Ming learning linear and quadratic equations. Traditional models like BKT act like a teacher with a very short memory. They only update the probability of knowing a single skill after each question. This approach loses a lot of valuable information. It can't remember that Xiao Ming struggled with a concept last week, or that mastering one skill helps with another. Plus, it relies on manually set parameters, which is both time-consuming and often inaccurate. Hello, everyone. Today, we're going to explore a fascinating concept in educational technology called DKT, or Deep Knowledge Tracing. Think of DKT as an intelligent teaching assistant equipped with a very special notebook. This notebook, powered by LSTM technology, acts like a memory conveyor belt, meticulously tracking a student's journey through their studies. The assistant performs three key actions. It forgets irrelevant information, takes in new knowledge, and outputs a snapshot of the student's current understanding. The ultimate value is its ability to predict a student's performance on the next question, all learned automatically from their practice data, without the need for complex manual rules. Let's break down the DKT model into its core parts. First, the input converts the student's action, like answered skill A correctly, into a numerical vector. This goes into the LSTM's cell state, our long-term memory conveyor belt. Three gates control the flow of information: the forget gate, input gate, and output gate. The result is a hidden state, a snapshot of the student's knowledge at that moment. Finally, an output layer takes this snapshot and converts it into a probability of answering the next question correctly. Now, let's get our hands dirty. We're going to simulate a simplified DKT calculation. We have our student Xiao Ming learning skills A and B. We've simplified the input encoding and model parameters for clarity. Think of the memory retention coefficient, alpha, as how much old memory we keep, and the new information absorption coefficient, beta, as how much new information we add. We start with zero knowledge, so our initial states are all zeros. Step 1. Xiao Ming answers skill A correctly. Our input is 1.0, 0.0. We update the long-term memory, cell state, by keeping none of the old memory, which was 0, and adding 40% of the new input. This gives us a new cell state of 0.4, 0.0. We then create a knowledge snapshot, hidden state, using the TAN function. Finally, we use this snapshot to predict the next probabilities. For skill A, the probability jumps to 63.5%. That makes sense. Step 2. Xiao Ming answers skill B incorrectly. Our input is now 0.0 minus 0.3. The LSTM keeps 60% of the previous state, 0.4, 0.00, and adds 40% of the new negative input. The new cell state becomes 0.204 minus 0.12. The knowledge snapshot reflects this mixed performance. When predicting PA, it dips slightly to 60.9%. Crucially, it doesn't drop to 0. The model remembers Xiao Ming's foundation in A. Step 3. Xiao Ming answers skill A correctly again. We repeat the DKT process. Keep 60% of previous memory, a success plus B failure, and add new positive input for A. Long-term memory for A becomes stronger, hidden state updates, and the predicted probability for A rises to 67.6%. DKT has learned the pattern of improvement. Unlike BKT, which only looks back one step, DKT looks back at the entire history. The LSTM cell state acts as a memory conveyor belt, allowing knowledge to accumulate over multiple steps. Even after a mistake, the model retains the student's prior successes. This is the mathematical realization of our teacher with a notebook analogy. So, what exactly is DKT learning when we train it? It's learning a set of parameters or weights that define how the model processes information. These include the weights for the LSTM gates, which determine how much to remember or forget, and the output weights, which map the knowledge snapshot to a final probability. The size of the hidden layer is like the model's brain capacity. And importantly, none of these are set by hand. They are all learned from data. How does this learning happen? It's an iterative process. We start with random weights. We show the model a student's data and make a prediction. We calculate how wrong the prediction was using a loss function. Then, using a technique called backpropagation through time, we figure out how to adjust each weight to make the prediction better next time. We repeat this millions of times with different student data, and the model gradually becomes more and more accurate. To sum up, BKT is a manual rule engine with simple states and limited memory. DKT is a data-driven pattern recognizer that automatically learns complex patterns from the entire sequence of a student's behavior, capturing hidden relationships between skills and even accounting for factors like fatigue or knowledge transfer. The power of DKT opens up exciting new possibilities. Its ability to handle long sequences makes it perfect for rich data like ebook logs. The hidden state itself is a valuable signal of a student's cognitive state. We can extend DKT by adding multimodal data, like eye tracking features, to the input. We can create gates that adjust the model's predictions based on detected cognitive states like fatigue. And we can use the model's output not just to predict correctness, but to directly drive adaptive learning systems, finding the optimal challenge zone for each student. In conclusion, DKT is a revolutionary approach to knowledge tracing. It models learning as a dynamic process, capturing the rich, sequential nature of how students acquire knowledge. Its ability to learn from data makes it far more powerful and flexible than traditional methods. As we integrate more data sources and cognitive science insights, DKT will continue to be at the forefront of personalized learning technology. Thank you for watching, and I'm now ready to answer your questions. Thank you for watching.